Okay, so in this video we're going to talk about linear functions. The learning objectives are to represent a linear function, determine whether a linear function is increasing, decreasing, or constant, interpret a slope as a rate of change, and then write and interpret an equation for a linear function. Graph a linear function. All right, so what's a linear function? Well, a function f is a linear function if it can be written as f of x equal to mx plus b, where m and b are constants. Note some special cases of when m is 0, the function is constant. We call it a constant function, and it simplifies just to f of x equal to b. If m is equal to 1 and b is equal to 0, the function is the identity function, f of x equal to x. All right, so if we look at what makes a linear function essentially a linear function, and compare it to something that's non-linear, we could see the difference. So let's go ahead and look at these two tables here. I have a function, linear function, in some order pairs, and also a non-linear function represented by a table of order pairs. Okay, so remember, the rate of change is the difference in outputs divided by the difference in inputs. So for a linear function, if you took the difference of consecutive pairs here, say 20 minus 10 here, you're going to get a unit increase of 10, or 10 by 10 each time this is happening. Okay. So what we want to notice though, if you continue this and do the same thing with the y values or the outputs, notice here we would get out from using these two order pairs. We have 100 minus 50, right? The difference in outputs there gives us 50. And we have 150 minus 100, that gives us another, what do you call, output of 50, or difference of 50 there, change of 50. And if you keep on doing this, you'll see that the y values are changing by 50 each time. Okay, and so for a linear function, if we're increasing by say the same amount, in this case by 10, we notice that the change in y is also changing by the same amount. In this case, it's positive because it's increasing. All right, but does that carry over with something that's not a line or a linear function? So once again, if you take two consecutive order pairs and look at the change in input here, we see that we get a change of 10 there, right? 20 minus 10 is 10. Here we get a change in output of 30 minus 10, which gives us 20. Now let's take another order pair there. Now we have 30 minus 20, so a change again of 10. This time we have 70 minus 30, which gives us 40. What you will notice here though, if you do this for consecutive order pairs, the change of input is staying the same, but the outputs are varying. So for instance, next here we have 130 minus 70, and so that increased that's a difference of 60, right? And then 210 and 130, that's a difference of 80. 310 and 210, that's a difference of 100. 430 and 310, that's a difference of 120. And then finally, 570 minus 430, that's a difference of 40. You notice that the change in y values are not staying the same. They are actually, in this case, increasing by 20. And that is not a linear function. A linear function does not do that. A linear function's change in outputs are going to remain constant if you're changing by the same amount of x, or inputs. So here, the nonlinear function, we have an input, we have a change in that's varying for every same change in x. or inputs. Okay, and so that basically is the difference between a linear function and a nonlinear function, is that the rate of change of a linear function is constant, and for for a nonlinear function, the rate of change varies. I didn't actually compute the rate of change, but you can see that happening if you actually do the actual division. Okay, so let's look at an example here where we're actually finding the rate of change for a linear function f of x. Okay, so by definition, a rate of change is just, you know, a difference in inputs. So, sorry, not difference in inputs, difference in outputs. Divided by difference in inputs. That said, well, okay, so let's take some arbitrary x values. So let's take x1 and y1 that are inputs for our function f of x. Okay, x1 and x2, and let's plug it in. So what do we got? Well, we have f of x2, that would be the input or the output for input of x2, minus f of x1, which is the output when we put an input of x1. That's the difference in outputs there. Now we divide that by the difference of inputs, so x2 minus x1. Once again, these are inputs, right, that we randomly just chose, x1, x2, this could be whatever here. And we want to calculate the rate of change. So that is the rate of change, but what is it exactly? Well, f of x2 really is m times x2 minus or plus b, right? That's f of x2 minus m times x1 plus b all over x2 minus x1. Okay, and so now just simplifying this here using some algebra, we'll distribute that negative. So we have this still. Okay, and we have some like terms. And if you notice there, b's are going to cancel, and we're left with mx2 minus mx1 over x2 minus x1. And notice that the numerator here has an m in common with both of those guys, so we're going to factor that out. And we're left with x2 minus x1 all over x2 minus x1. And notice that factor of x2 minus x1 cancels the factor on the bottom. And we're entirely left with just m over 1, or just m. So notice the m there is the rate of change, which happens to be the slope of this particular function, or the line. So if you remember, this has the form, this f of x, mx plus b really is just y equals mx plus b. And of course we have studied lines, and m is just the slope of the line. So the rate of change is just the slope. And for a linear function, the rate of change is constant, and it's because the slope is constant. Okay, and we showed that the rate of change equals m. So the slope of m of a linear function, f of x equal to mx plus b, is given by m equal to the change of inputs divided by the change in, the change in outputs divided by the change in inputs, which is the formula f of x2 minus f of x1 over x2 minus x1. And that's your slope, which we knew, before that was just y2 minus y1 over x2 over minus x1. Okay, once again, x1 and x2 are just two different inputs, and the domain and range of a linear function is negative infinity to infinity, So note, in applications, the domain is sometimes restricted, and we'll see an example in this set of notes here. All right, the next example here, we're asked to graph the function f of x equal to negative 2/3 x plus 1 and determine the slope. All right, well, from the previous calculation, we know that this is just a line, right? Y equals negative 2/3 x plus 1, and the slope there is m equal to negative 2/3. So we know the slope. Now, one thing is, well, if that's the case, then this plus 1, it has to be the y coordinate of the y-intercept. And so we know that we have a y-intercept at 0, comma b, in this case 0, 1. So plotting this here, I would have a point at 0, 1, and then we would have a slope of negative 2/3. And so I would go down maybe 2, go down, have a rise of going, or a fall of 2, and then a run of 3. So 1, 2, and then 1, 2, 3. So I get a point there. Or I could have went up 1, 2, and then over to the left 3. 1, 2, 3. Long as it forms a line that has a negative slope. All right, so we get something that looks like this here. And that's our line of our function f of x equal to negative 2/3 x plus 1. All right, next example here, we're asked to find the formula for our linear function that satisfies f of 9 equal to 4 and f of negative 1 equal to 2. All right, so we have these particular equations, if you want to, that the function needs to satisfy. In fact, they're telling us the order pair, right? F of 9 equal to 4 tells us, well, we have an input of 9 and then an output of 4. So that just basically corresponds to the point 9, 4. Likewise, f of negative 1 equal to 2, we have again an input of negative 1 and an output of 2, which corresponds to the order pair of negative 1, 2. Okay, so we have two order pairs, and we know a linear function is just a line, right? Y equals mx plus b. We can find the slope of a line using our definition above, right? Or the rate of change, f of x2 minus f of x1 all over x2 minus x1. All right, so this first order pair here, we'll call that x1 and x2, or x1, y2, or f of x1. The next order pair would be just to think simpler, x1, y1, x2, y2. Okay, so this is once again y1, and this is y2. All right, so what do we have? We have y1, which is, this is y2, this is x1. Got my indices all mixed up. Okay, so let's plug our values into the formula. So we have 2 minus 4, and then negative 1 minus 9. So that gives us a negative 2 over a negative 10. And we can reduce that fraction by dividing out a negative 2, which gives us 1/5. All right, so now we have the slope. Now we could use our y minus y sub 1 equals m times x minus x1. In other words, the point slope form of the line. And where we know that y1, and we already called y1 what it was. We gave that the value of 4, right, for that point. And then the slope we just calculated to be 1/5. And x minus x1. X1 is 9. Okay, so then now we have y minus 4 equals 1. I'm going to distribute the 1/5, so 1/5 x minus 9 times 1/5 is 9/5. I'm going to go ahead and add 4 on both sides. And of course, we need to find a common denominator. Well, 4 is the same thing as 20 over 5. So then we add to get y equals 1/5 x plus 11/5. And of course, we're using function notation here. We probably don't want to call this y no more. Well, we could rewrite that as f of x. And let's go ahead and box that there. That's our linear function there. All right, let's move on. Interpretation of m and b. In other words, what is it? Well, of course, this is the slope or the rate of change, and b is the y-intercept. Okay, and the reason for that is, well, if you evaluate a linear function at 0, then f of 0 equals m times 0 plus b, which simplifies to b. So graphically, this just means b is the y-coordinate of the y-intercept. However, in applications, sometimes b is what's called an initial condition. Another initial condition for an input of 0. For example, suppose f of t equals mt plus b represents the position of a point on a real number line at time t equals 0. So, I mean, think of a real number line. I mean, I don't know where it starts, but here's a real number line. And that value, the f of t function just represents wherever this point is here, that's f of t, with that value at time t. Okay. So then f of 0 would be where, say, suppose it was right here. So if that happened at t equal to 0, then that x coordinate or that time coordinate, or sorry, the time is 0, but the value or its position on the real line would happen at b, at time t equals seconds. All right, so that's one interpretation. It's usually some type of initial condition. Sometimes it makes sense, and sometimes in applications it might not. But as we know, the slope m is the rate of change, and the rate of change can be thought of as some kind of ratio as well. You can also think of m, right, or you get the slope as m or m over 1. So as there is the change of so m is the change of output per unit increase in input. So for example, suppose we had a function c of x equal to 25x plus 3500 is the total cost in dollars of producing x units of a blender. The slope of 25 tells you that the cost of producing each unit is $25. Equivalently, for every additional blender produced, the cost increases by $25. So that's in typical interpretations of slope, okay, there, for a line or for a linear function. All right, so here where x is, we have f of x equal to mx plus b. Determine if the function is increasing, decreasing, or constant. Well, from earlier, we know the rate of change is how much if it's related to if it's increasing, decreasing over a given interval, okay, and overall on average, if you want. And so we know that if m is 0, then it's basically constant. In other words, it's not going anywhere because you have 0 change in y over the change in output. So you have a 0 change of output, right, for every unit increase. So it's constant in this case. Now, if m is positive, if m is positive, we know that the rate of change is positive, which means it's increasing. If m is less than 0, we know that the rate of change is negative, so therefore it is decreasing. Okay, so it's very easy to determine if a function is, a linear function is increasing, decreasing, or increasing over any given interval. In fact, it's increasing either increasing on its entire domain, or it's decreasing on its entire domain, or it's in fact constant on its entire domain. It's either one of these situations, because remember, the domain is negative infinity to infinity, and the rate of change or the slope is always constant, and it doesn't change, right? It's always a constant value. And so in that case, and here I mean in constant is and kind of you might be getting confused when I use the word constant there, but constant here, a constant rate of change is always happens with a line. But if we know a line is constant if m is equal to 0 when it's flat across the horizontal line, it's horizontal, right? It's increasing if it looks like this, right? Positive. So that means it would be increasing, and then of course this would look like more of a decreasing because the rate of change there would be negative. All right, I think we killed that example. Let's look at an application here. One way to estimate the ideal minimum weight of a woman in pounds is to multiply her height in inches by 4 and subtract 130. Let W be the minimum weight and H be a woman's height. So A asks us to express W as a linear function of H. B, find the ideal minimum weight of a woman whose height is 62 inches. C, find the domain of the function. All right, so A here, we're going to express our weight function. It's a function of H. And what you do is multiply the height by 4. So 4h, and then subtract 130. And that will produce the minimum weight, or ideal minimum weight. All right, so B here, we're actually finding the ideal minimum weight of a woman whose height is 62 inches. So we just plug that into our function. So W of 62 is 4 times 62 minus 130. And let's go ahead and do that calculation. I did it freehand here, so I got, let's redo it, make sure I got the right answer. 62 times 4 gives us 248, and then subtract 130, which gives us 118. All right, so what does this mean? The ideal weight. For a woman whose height is 62 inches is 118 pounds. All right, so C here, we're actually to find the domain of the function. Now, if we consider the line, it's just a linear function, and I told you it's negative infinity to infinity. Well, that somewhat does not make any sense here because negative values wouldn't make sense for the input. We don't have, say, women whose height is, say, negative 62 inches. So what we do is kind of make sense of the application. And let's go ahead and use Desmos to graph this function. All right, so let's plug in our function. So W of H equals 4H minus 130. Okay, so by default, it's not going to be shown here just because the fact that it's out of our range here, our window. So I'm going to zoom out, and there we go. We see it there. And we're looking for, if you notice, the y values or outputs that are negative don't make any sense. Okay, so and they don't start making sense until we get to this point here, which says, okay, kind of don't make any sense there anyways, but the x-intercept here, or in h-intercept, we get 32.5, and that gives us an input there. That's now after 32.5, you can see that the outputs will start getting positive or become positive. Okay, so that let us know that we probably want to take a domain to be, let's go back here, the domain, and in set-bit notation, the set of inputs H, such that H is probably, we want that probably to be greater than 100 and 900. What was that? 32.5. However, the closer you're to 32.5, it still kind of doesn't make sense in application here, because you don't want someone weighing, the ideal weight to be 0 pounds. Don't make sense. And but at least the outputs would make a little bit more sense for values greater than 32.5. So the domain, in interval notation, can be expressed as open parenthesis 32.5 to positive infinity. All right, so that's that example. Next example here. The value V of a molding machine T years after it is purchased is negative 4,000 T plus 58,500. It should be saying V of T, where T is the input and it ranges from 0 to 5. All right, explain what the V-intercept and slope-intercept are. Okay. Well, the V-intercept, which means that it would, if we would graph this, we probably would see something like this here, and then adds a input of 0, right? We'll get the value 58,500, and it has a negative slope, so it's going to start looking like this somewhere. All right, so what does this mean? Well, it's just the initial cost of this molding machine. So at time 0, V is 0, gives an output of 58,500. Okay, so it's the initial cost to use this of this initial vending machine or molding machine, excuse me. All right, what about the slope? Well, the slope is telling us that, well, what is our slope? Well, it's negative 4,000. And so the value of this molding machine is changing by negative $4,000, I'm assuming here, for every unit increase. So for every year, it's depreciating by negative 4,000. You can think of it over one for every year. Okay, so that is what we would call its annual depreciation, because for every year it's decreasing by $4,000. And so that's the annual depreciation. Okay, that wraps up this video.